vapor intrusion, challenges and trends. Our experts today are our own Frank Clark, a professional engineer, and Chris Thompson, a professional engineer. Thanks, guys, for joining us today.
Glad to be here.
So before we get started, I wanted to go over a few housekeeping items. If you have any questions, please send them to us through the chat tab on your GoToWebinar window. And our executive producer, Lydia Gross, is going to ask the questions, and we'll get those answers to you as soon as possible. If we don't get to your question, we'll make sure that Frank and Chris sees the question and he gets an answer to you very soon. We are recording this webinar, and it will be available to rewatch on our website soon, along with the slides. And we will send you an email with the link when they are made available. So let's get to it. So first, I'd like to introduce to our experts today, Frank Clark, who has done a number of these. Frank, how many do you think you've done? 5, 6, 12? Not that many?
A few more than that.
A few more than that? Okay. Yeah. So, yay. So he's our principal engineer at Braun INTERTEC with 39 years experience in the U.S. and overseas, working on assessments and remediation on contaminated soil and groundwater. For the past 24 years, he has been working in Texas and for property assessment and remediation under various Texas regulatory programs such as voluntary cleanup, leaking petroleum storage tanks, innocent owner programs, and MSDs, our favorite. He's been a licensed engineer since 1986 in Texas and Maine.
Mm-hmm.
I was going to say Massachusetts, but you're a Boston guy, aren't you, though?
Mm-hmm.
Okay, well, good. Well, thanks for being with us again, Frank. So appreciate it. And Chris Thompson, he's also a professional engineer. He's a vice president and principal engineer at Braun INTERTEC with 37 years. So between the two of you guys, we have this topic covered, I think. So he has designed an industrial dust and fume control systems, industrial makeup, air systems, soil vapor extraction, and vapor mitigation systems since 1983. And he's been practicing registered engineer since 1987 in Minnesota, Illinois, and Nebraska. I know I'm getting all my states.
These state acronyms are good. Yeah.
Vapor mitigation system designed in Washington State, Texas, California, Minnesota, and Wisconsin. So we have a lot to cover today. So I want to let's get started. So. Frank, are you going to be talking with the first slide?
Sure, right. And thanks everyone for attending. Just to kick off, many of you may have attended previous webinars that W&M has had. We've had a number of these over the years dealing with vapor intrusion. Some of them focus more on vapor assessment. Today we have the benefit of having a vast experience of Chris Thompson, who's been working on vapor mitigation systems for decades, and that's not an exaggeration. So he has loads of experience, and he will be sharing some with us today. I'll kick it up and just go through some of the basics of vapor intrusion and what we'll be talking about before I hand it over to Chris to talk about mitigation. First of all, what is vapor intrusion? And for purposes of this presentation, it's the intrusion or migration of VOCs from contaminated soil or groundwater into an enclosed structure. Many of you who have worked on environmental projects, in particular phase 1 environmental assessments, might be familiar with another term called vapor encroachment. We're not speaking about that today. That is a term that is defined by ASTM and is really just the presence of vapors in the subsurface that could migrate that have migrated from a contaminant source. We're taking it the next step, not encroachment, but intrusion into a structure. So what chemicals are we concerned about? I'm going to call these the usual suspects. If you're involved with environmental consulting, you know that these are the compounds that can be most problematic on many of our sites. VTEX compounds have been a thorn in our sides for decades, from leaking underground storage tank sites. Trichloroethylene, or TCE, is a very common degreasing solvent. We see it on a large percentage of our commercial and light industrial properties. With regard to vapor, TCE is particularly problematic because it is a carcinogen and it has very low inhalation targets. So it is often a driver when it comes to mitigation requirements on vapor intrusion properties. Tetrachloroethylene, PCE, or PERC, is a common dry cleaning solvent. Everyone's heard of that. Even though today dry cleaners are migrating away from PERC to more environmentally friendly solvents, we still have a legacy of thousands of historical dry cleaning facilities that used PERC in the 50s, 60s, 70s, and 80s. And we all know about projects where these types of releases from these small dry cleaners have created a lot of problems. And then in addition to these larger quantity VOCs, we have all types of other cleaners such as carbon tetrachloride, methylene chloride, MEK, a paint stripper. These are found in a number of products and can be found in contaminated soil and water. And methane, which has been an issue for quite a long time, typically associated with landfill gas, but we have also had projects very recently where organics, for example, from a buried pond that was filled in were degraded, and the organics created sufficient methane to be a problem in an overlying proposed structure. And also oil and gas wells, improperly sealed oil and gas wells can allow methane from very deep strata to migrate up to the surface and affect overlying structures. So a brief conceptual model for mechanisms of vapor intrusion. The source area is often contaminated soil, contaminated groundwater, sometimes separate phase product that we call NAPL. And the concept is that these volatiles will volatilize and rise up through the soil mass into an overlying structure, kind of like hot air. In reality, we know this is a simple model that helps us get our heads around what might be going on, but we know that in truth, it is much more complex. There's lateral movement in the subsurface due to layering, sedimentation of soils, presence of impervious clay layers that might inhibit or push migration of push volatiles off to the side, presence of cracks or fissures in desiccated clay layers, which are found commonly, and the presence of utility conduits, which are lateral or linear features that are often backfilled with pervious material and can allow VOCs to migrate great distances from source areas. So these are all complications in the vapor intrusion conundrum, and things that we have to deal with, and we'll be talking about a little bit.
So, Frank, sometimes, these soil contaminants, the VOCs underneath, I mean, so let's say when they were building those houses, you know, there may not have been a vapor intrusion when you have done a test and they say, hey, there's no vapor intrusion, and then all of a sudden, because it takes time for that vapor to come up, and have you seen?
Sure, and contamination migrates, as we know. Groundwater can migrate, does not respect property boundaries, so it could migrate from an adjoining dry cleaner or gas station to an adjoining, the nearby residential neighborhood. So it might be something that could take years to migrate, and therefore you wouldn't know it. And typically for residential developments, you would not be testing for this type of issue. Typically only happens on commercial developments. So here we just have a few pictures. These are some of our jobs where we've done vapor intrusion assessments. On the left is a crack in a large warehouse slab floor that settled due to poor soil conditions. And when we did screening, we did find that volatiles from a subgrade plume were migrating into this large warehouse. And the upper right was an assessment of a standard Texas warehouse in this case, and you can see there are construction joints and expansion joints, and generally when constructed, these joints are filled in with some type of caulking or filler, and over time this caulking or filler will degrade, or in some cases just be absent, as you can see from this photograph. And these are other avenues of potential vapor migration into a structure. And the lower right is simply a picture of a sump in a concrete floor, and again, an open avenue for subgrade vapor to enter into a structure.
Frank, this is Chris, and we recently did a test on a building with a smoke pan, and you can literally see the intrusion of air into the building space when the building HVAC systems are operational.
Yeah.
So it's very evident in some cases.
That's a good example of a picture is worth 1,000 words. To physically see the smoke migrating into your space is really tells the tale. Yeah. So why has vapor become such a big concern? If you think about typical contaminant investigations, we're looking at soil or groundwater, and we have to have a contaminant in a media and then an exposure route to a receptor. So in the case of a typical investigation, you have to drink or ingest contaminated groundwater, or you have to come into contact with contaminated soil, or perhaps inhale vapors or inhale dust from contaminated soil in order to have an exposure. So there's a process of from the source to the recipient that must occur for there to be a risk. With vapors, we have a kind of a unique situation that if there are vapors within a structure, then if you are breathing, and we are all breathing many times per minute, then the exposure route is complete. So it's an immediate exposure route, and therefore can be really problematic because of the ingestion of volatiles into your lungs.
Yikes.
Yeah. So what are some of the difficulties? I'm not going to go through these bullets one by one, but there's lots of variations in subsurface conditions, which is a problem we deal with on all types of subsurface projects, be they geotechnical or environmental. The nature of the contamination will vary. What chemical is it? How concentrated is it? How deep is it in the soil? What's the stratigraphy, et cetera, et cetera. And when you think about another factor that we've added to this is the fact that buildings are constructed using a wide variety of protocols depending upon when they were constructed and for what purpose. So you can imagine a building, for example, built in 1950 would not have all of the airtight concerns that we do in LEED qualified buildings in 2020, which are often airtight and are built to avoid to keep HVAC costs low, et cetera. So all of those factors associated with different building types will dramatically affect the opportunity for vapors to enter the structure. And then we have the preferential pathways, which is a real troublesome aspect of many of these sites because they could be small linear features of sand during backfilling or during installation of shallow utility trenches that can be pathways for volatile to enter a structure. We're not going to talk very much about sampling because we've done that during previous webinars, but I thought I would just share a slide that shows a typical sampling setup that we use frequently and is very cost effective using vapor pins where we can just drill a 5/8 inch diameter hole through a concrete slab, insert a brass sampling pin, and then are able to sample soil gas from beneath the slab. And the beauty of this type of installation is it's very low disruption to the tenant. Here you can see we just had to pull back a carpet tile, drill a hole, put in our pin, and then we have a flush cover on it, and then we flap the carpet tile back on, and no one even knows we've been there. So for occupied buildings, there's a mechanism to go in and get sub-slab vapor samples without disrupting the business or the tenant, which is a very big deal for some clients. So going from subslab to indoor air, we all know that once you have a potential for vapor intrusion, then indoor air sampling is a logical next step. And we'll give you the best indicator of really our volatiles entering at levels that could be problematic. And we can compare those indoor air levels to criteria established by state or regulatory authorities. We have to be careful that indoor air sampling can vary seasonally and due to a lot of variables, atmospheric pressure, and even over the course of a day. There have been studies that have shown that concentrations of TCE, for example, in one study varied, I think, by a factor of 5 over the course of just a half a day using continuous air monitoring. So a lot of things can complicate our assessment of vapor. And background issues also come into play. And if we go to the next slide, we'll show some of the sources of contamination. We all probably have a closet in our laundry rooms or garages, or that looks like the one on the upper left, filled with chemicals that we use for routine cleaning, pesticides, cleaners, aerosols. Many of these contain VOCs that can result in concentrations detectable in ambient air. Dry cleaning, there's been multiple studies have shown that recently dry clean material in a single family house will result in the detection of dry cleaning solvents in the air. And then gasoline used for lawnmowers or generators. There have been studies that have shown that even in a garage, a gasoline can sitting in a garage adjacent to a single family structure, that they will find evidence of BTEX within the air in that single family home. So all complicating factors that make the job just a little more challenging. Yikes. So now I think we have a quick poll that's kind of fun to do to see what people's thoughts are with regard to vapor. What % of the time would you expect to find potentially harmful VOCs in a structure? This would be just detectable concentrations, not above any regulatory threshold, but just detectable by a lab analysis. 10%, 25, 60, or 80. So I think, have we launched the poll? Okay.
And while people are voting, I thought I'd point out, those slides you show somewhat are applicable to single family homes, but in reality, commercial and industrial facilities all have this very similar potential of indoor VOCs.
Absolutely, yes.
All right, go ahead and close that poll. And do we have any?
All right, let's see what the results are.
I'm going to guess. Can I guess? What percent of time you spend from station? I'm going to say 25%. That's my guess. A very uneducated guess.
10% of our audience said it was 10%. We had 33% say it was 25%. 38% said it was 60%. And 19% said 80%.
Oh,
ooh, all
not
right.
Too bad, not too bad. Well, here's the results of some studies. If we go to the next slide, this is my last slide. Well, EPA did a study and reviewed 18 indoor air studies across many states. This is a while ago, but still, I think, applicable. And they found that over 80% of the studies reported the presence of BTEX in indoor air, whether that was from an actual vapor intrusion issue or due to ambient contamination. I'm not sure they concluded, but that is a surprisingly large percentage. So kind of amazing. And 40 to 60% detected one of the chlorinated VOCs in indoor air. Again, a very large percent. So when we're doing vapor studies, we need to consider background concentrations as part of the process. So with that, I'm going to turn it over to Chris, who is going to share some of his experiences and discuss the challenges associated with mitigation design for vapor intrusion.
All right, well, thanks, Frank. So what I want to cover is an overview of mitigation alternatives that exist out there, discuss a little bit about the design and construction process for mitigation, and just show some information about the components of mitigation alternatives, and in that process provide some lessons learned that we've found over the years. And I start out with this slide, remediation versus mitigation, just partly because people mix up the terms and get confused by what they might be required to do or what they're having to do. And as a responsible party to a contaminated site, you may be required to remediate the source of VOCs. And in the process, you may also need to have some mitigation of the building. And typically you can do both at once, if you will, with the same system. We have that kind of systems in place. But as a voluntary party or neighbor to a contaminated site, which now you have migration vapors onto your site, you may just be mitigating. Mitigating, is the definition I put there, is you're just trying to cut off that exposure route in that sub-slab area of your building, or even to the sides of a basement of your structure. Again, cut off the potential for that intrusion. Maybe blocking utility corridors, it may be putting some other type of mitigation system. So next slide. So depending on what regulatory program you are in, state you're in, and so forth, generally there's sort of 5 main mitigation alternatives that you may have a selection of, if you will. There are variations on these, but generally they're a passive barrier system, maybe an active subslab depressurization, active subslab ventilation system, and there's a minor difference there. Other things that have been looked at are trying to modify your building, pressurize your building to reverse that potential for intrusion to occur, or repairing your floor, filling those cracks that Frank showed earlier, and blocking utility entries into the building. As I indicated in our last month's blog about vapor intrusion, those 2 steps can prove to be quite difficult. So I'm going to just focus today mainly on those top 3, and for the most part talk about commercial and industrial buildings, but they very well apply to other types of structures, especially multifamily housing, maybe mixed commercial and housing, which there's a lot of that type of structures these days. Next slide. So the idea behind those 3 main alternatives are, as I show here, a passive barrier system just to block that exposure route. You're not trying to collect the vapors that are below or to the side of that building, but you just have this physical barrier through which those chemicals can't pass. And you can think of it as like a vapor or a water barrier, which sometimes are used and called out in building codes for buildings. But I would just point out that a vapor barrier called out in a building code in an occupied portion of a building usually is a very thin plastic membrane, maybe 6 mil thickness, if you know what that term is, and doesn't typically work. So pressurization system versus ventilation system, generally that difference is that a subslab ventilation system has added to the design a permeable ventilator, and also allowing fresh air into that system. And we'll get into that in a little bit, but other than that, they're both were active systems, essentially pumping air from beneath the structure and sometimes to the sides and discharging that air to the outside. So, next slide. I would just point out, however, that in the state of Minnesota recently, and it's now part of a guidance document in the state, and another alternative is the addition of a parking structure as an alternative for vapor mitigation. In the past, for projects, it was assumed to be a valid alternative. Hey, you've got an underground parking structure, that's going to block the vapors from getting into the office or apartments or condos above. It was found, however, that is not the case. And so parking structures now with certain design and construction modifications are allowed. We are very familiar with this because we here at Braun actually developed this document and did quite a bit of research, and we had some principal architects on staff here that are very familiar with how buildings are sort of living, breathing organisms, if you will. And so anyways, I just point that out, that actually is somewhat of a variation on vapor mitigation alternatives. So once you're into a scenario where you know you need to mitigate, and different states have different requirements for going through the testing, as Frank was pointing out, but you're really you're designing a system to be incorporated into some kind of building or structure, and you need to get that system thought through, designed, and constructed so that it operates as you planned. And so whether you kind of think through it on like a focused feasibility study or not, you're usually going through all of these issues in some form or another. And as Frank pointed out, there are a lot of differences in building construction techniques and how buildings were built, how new buildings are going to be built, sort of what the source strength is of the contaminant. Do you have a source down there, or do you have just some residual vapors in the soils? A lot of regulatory programs don't really take that into account. You monitor for subslab vapor, and here in Minnesota, for instance, you do it in the heating season, you do it in the non-heating season, and come to a conclusion that you do need to mitigate, but there's not a lot of information about, well, how much mass is really down there. But you go through this process and come up with a plan for mitigation, and it may be just a barrier membrane, it may be a depressurization system, and it may be a ventilation system. And again, there are certain regulatory programs that don't allow just a straight vapor barrier membrane. Here in Minnesota, for instance, as a standalone mitigation alternative, those aren't allowed. So, next slide. So overall, the whole design construction process is really there to make sure that you're selecting what's appropriate for an alternative, that you're designing and constructing it so that in the end, when you're having to test that system or essentially operate it and monitor the system, it's working as you hoped it to. And if, again, depending on the system, this may be a very minimal effort, but it can be much more complicated where you have many plans, pages of engineering plans and specifications all laid out, and a construction contract for the contractor or contractors that are building this. In many locations, you have one contractor placing piping beneath the floor and a plumber doing any plumbing of piping above the floor, having to do with union rules and who can do what. So the overall process, if you will, is come up with a basis of a design. What are you trying to do? What should this system look like? How are you going to construct it? How are you going to test it? It's permitting requirements and long-term reporting. Many states have environmental covenants that if you have an active system, pressurization or ventilation system, that you're going to have ongoing, likely annual testing and reporting, or at least documentation that the system is still operating and reporting. That goes along with a property deed, and you kind of can't hide from that. So again, it just points out the need to making sure that you're approaching this properly. Next slide. The next slide was supposed to have some graphics to it, and not showing that way.
They were really cool, by the way.
It really, this could be either a depressurization or a ventilation system. In this case, I'm showing it as a vent system with fresh air into the system. It comes in on one side of the building. Think of this as a 200,000 square foot building. And you have little 4-inch PVC pipes along that far side. Fresh air is coming in. It's being drawn in because there's a fan somewhere there where it says vent riser pipe. And the fan is drawing air along that header pipe. So the blue air is turning to red, picking up any potential vapors that are rising, say, up from below. This would be in the case of like a sub-slab or a slab on grade building. And so conceptually, all you're trying to do is draw air from under the building and discharge it somewhere above the roof. And that's a real typical depressurization or ventilation system. If I had a graphic for a depressurization system, I'd probably show that a point going through the floor of the building, maybe right in the middle. Typically, they're called suction pits. Sometimes people put in perforated piping, but a lot of times it's just a suction pit, and you would have radial flow to that point. So anyways, that's too bad that we're not seeing movement on that. Next slide. So there's a lot of components of a depressurization or ventilation system, and it's the design and the construction of those things that are going to make a system successful. And that's where we've learned lessons over the years and learned what works, maybe what doesn't work. I listed all these components, not in any particular order of importance, but I just thought I'd go through some photographs of some of these systems and point out some issues and lessons learned that we have. So next slide. I start out with this. It's showing a vapor barrier membrane being constructed. A lot of times they come as rolls, and they're like 12 feet wide, 100 feet long. And for a big building like this, as shown, you need to lay them out, tape or seal them together so that they don't leak. There are sprayed-on membranes. There are rolled membranes. Typically, the rolled membranes are 15 or 20 mil thick. And a spray-on membrane, I think, might be closer to 60 mil thick. So this could be a passive barrier in a building. And we can do this in existing buildings or new buildings. Existing buildings, however, that's a fairly unique situation where that happens. But we've been involved in a couple where that has happened, where the entirety of the floor of the building was being taken up. In the case of the one I'm thinking about, they were lowering the basement floor such that there's greater headspace in that basement room. And so we were able to put a membrane in after the floor was removed. So this picture, just go back one second, that picture also shows some piping being placed in the soils there. In this case, it was being placed in a dense sand layer. And then that pipe is a perforated drain tile HDPE pipe. It has a sock around it, a legit textile material that keeps any fines, to the extent there are fines in those and sands, out of that pipe. Because the holes in the pipe are relatively large. The next slide, and the next slide is the same kind of setup, showing the sealing of the membrane. In this case, there's a textile felt material being placed over the membrane because the aggregate base for the new floor of the building is being placed right over the membrane. And we have done some tests and found that that aggregate base, because of the sharp rocks, in Minnesota we call it Class 5, Illinois it's a CA6. It's an aggregate base and goes by different names many times coming out of the Department of Transportation terminology. So anyways, putting that geotextile material over as a protective layer, and you'll notice that there's a guy walking on the membrane, but the trucks aren't driving on it. And one of the big things through that whole design and construction process, and that we've gotten pretty darn good at, is meeting with, say, the developer, the general contractor, the subcontractors doing this work, to make sure that they're not driving on the membrane or driving over where the piping might be. We've had to go back by hand, dig up and repair piping that the guys were just driving over because nobody ever told them they couldn't. And it's just amazing what people do if you don't communicate up front. So that's a picture. So this is just a sort of a section through the floor, generally, of a ventilation system, showing the concrete slab, that aggregate base, the geotextile, the fine filter vent sand. People use some different things for that. Sometimes it's more like a P-rock, but there's some reasons not to use that. And then vent piping in the vent layer. In this case, the project had extra ag base on the site. It was actually recycled concrete from an old building. So we were able to place that over the contaminated soils. And there was also contaminated groundwater below, and create this sandwich, if you will, where any potential vapors getting through that lower class 5 would get into the vent layer, then through the application of vacuum into the pipes and be sucked out of there. And by not drawing very much vapors from below, but only those fresh air coming in, the fan for that system is a very low fractional horsepower fan, and we get many flushings of that zone out per day. I mean, so we were lucky that we had that additional material. It also provides somewhat of a barrier to vapor rising up. Next slide. In many cases, we don't have the luxury of building things up, and this was a site in California where the client did not want to expend the cost of bringing more soils in. So we went to a very thin vent layer and a flat pipe. And if you don't know what a flat pipe is, it's typically about an inch thick, and it's about 12 inches wide, and you can convey a lot of fluid through that pipe. And that could be water or it could be air. And the flat pipe isn't everywhere under the floor. It's just like the round pipes you've seen. And the air is conveyed through the vent sand into the pipe, which is under a vacuum on its way out. So different buildings, different setups have different needs. One of the things we've learned is if we can, we want to put the membrane where we have vent systems, or we're putting in a membrane, put it as deep as we can below the finished floor elevation of the building. One of the reasons for that is as buildings use changes, there may be tenant improvements where they're, say, moving plumbing piping around. And for at-grade buildings, that means they're going to be digging down a couple of feet. So where we can, we want to keep the membrane and that piping 2+ feet below the finished floor elevation. It really can be helpful in the long run as, again, buildings use are changing. So next slide. So that vent layer, just maybe here's a typical grain size distribution based on what are called US sieve sizes. That lower, that number 200 sieve, that is material that's a very small diameter, and we want minimal amount of that material being able to pass that sieve. And that's why those numbers are so low. That's generally, according, describes a fine filter aggregate. And we find that works very well. It's somewhat counterintuitive that someone says, well, you should use a P-rock. And if you go to the next slide, that's more along the lines of what some people consider a P-rock, small pea-size individual grains. This picture on the left shows the buried vent pipe. There's some safety glasses there for some scale. And there's a hole in the vent pipe, and there's a series of those along the length of the pipe. Close-up picture on the right shows that the individual grains, they actually can fit into that hole. Not a good thing, because the pipe is getting covered up and surrounded by that P-rock. This was a case where we were being brought in as a third party to review things on behalf of a tenant that was going to move into this building, and they actually were eventually going to buy it. And so we were documenting issues as things were happening, and we couldn't change things, but we could just point them out. And other issues that came up that really kind of go back to that design process, along with this issue. There was no sleeve on that pipe. The vent sand and the holes in the piping weren't compared to understand that there may be a problem, and other things that happened on it. The contractor, instead of having a 6-inch vent layer, he thinned out the layer in some areas due to some other construction issues, such that there was hardly any vent layer there. Well, the vent layer acts like a pipe. It needs to convey the fluid to the air, and so it needs a certain capacity. Other things that happened were they were above ground piping had some valves. They were brand new valves, and the valves they typically have a plug in either end of the valve open. So they left plugs in, and then they plumbed up the system, and there was no flow. Then this was in the case of fresh air inlets. There was no flow coming in from some of them. And by process of elimination, we were finally able to figure out, well, maybe that's the case. Sure enough, they opened up things, and oh, I'm sorry, we left plugs in. So the other thing they did, and we'll get to that in a few minutes, is the discharge of the system up on the roof of the building. Typical guidelines talk about keeping those discharges so many feet away from your inlet of some kind, say for an HVAC system. They had no idea about that. They plumbed it right next to inlets. They also plumbed it right next to a bathroom vent outlet. And in the case of this system, it was actually going to be started as a passive system, and passive systems can operate in 2 directions. So air can be sucked in at that vent up on the roof of the unit. So it was very potentially going to suck in the discharge coming from the bathroom vents, which was a little bit uncomfortable. Again, goes back to the very beginning of the design process, defining plans and specs, and communication, whether it's on the back of a napkin or whether it's spelled out in a document that's a couple inches thick. It needs to be spelled out so everybody knows what they need to do. Next slide. So this was, I'm just showing you some examples. This was a passive ventilation system. The red lines are extraction piping with extraction vents running to the roof of this building. The whatever color that is, blue around the perimeter and down the middle are where fresh air is allowed in. And I bring this up because it's a passive system, and while it's not allowed here in Minnesota, it actually works. It exchanges the air on a fairly regular basis, and it's all based on wind, thermal gradients, and wind across the roof of the building. And you get a vacuum everywhere in the building, you get airflow, and it very much can work. Next slide. So this is a very similar building, but with an active system below the floor. And again, we're looking at a plan view, looking through the floor, through the membrane. Beneath the membrane, we're seeing the fresh air inlets, which are down on the bottom side of that building, because those are the truck docks, hard pipe all the way around to the other side of the building, where the air is allowed in, or it's allowed in on the south side also. And the extraction pipe is down approximately the middle of the building. One thing we've learned is we want as much symmetry as possible in these systems. And it's especially true for ventilation systems, for the pressurization systems, depending on how you plumb those things, it can be very true for those also. And so there's less piping than the passive system. And another thing we've learned is the cost of all of those vent risers to the roof of that building for the passive system actually, gets pretty great. You have the materials and you have the construction and so forth. And in this system, the sub-slab vent system, we have one blower you can keep this, and leading to the roof. When that blower turns on, here's a mapping of the vacuums underneath the membrane. We have a series of vacuum probes we've put in. Frank showed you the vapor pins used for investigation. Those same things are typically used for monitoring vacuum beneath the floor. We actually, on some buildings, go away from those because we've got clients saying, I don't want you to drill a hole in my brand new floor, or that's not a good location to put that because I've got a tenant and a daycare here or whatever. For a new building, they're easy to put in. So we have a series of those, and here we show what those vacuums are. And these vacuums happen to be given in pascals, which is just a different unit. For a sub-slab depressurization system, used to be for ventilation systems in the state of Minnesota, all we need is about 3 or 5 pascals everywhere under the building. And we've got more than that at those extremes where the fresh air is coming in, and we've got way more than that along the extraction vent, 600 pascals. And where you have flow, you've got a vacuum. Alternatively, I'd point out where you have a vacuum, you may not have flow. And that's maybe another benefit where when you can do a ventilation system and you do have a significant source of the VOCs beneath or to the side of your structure, you may want to go to a ventilation system because you for sure are removing mass from beneath the building. Depending on the soils you have at your site, if you have very tight clay soils, you may not get much flow, even though you've got great vacuum. You can sort of think of this as if you suck on a straw and put your finger on the end of it. You have great vacuum in that straw, but if your finger's completely sealed on the bottom, you don't have any flow. You start to open up your finger, you start to get some flow. Anyways, next slide. Another thing we've learned is we've been monitoring the loss, the pressure loss, the head loss of flow of the air through the vent stand. And we have found that we can draw air from the one side of the building all the way to that other side of that building and get 1, sufficient flow, 2, sufficient vacuum, even though now in the state of Minnesota, one of the metrics for monitoring a sub-slab ventilation system, we just have to show there's flow. We don't have to show there's vacuum. Quite sure how it ended up that way for recent guidance that they published, but that's the case. But we know that we can get that at least minimum and quite a bit more than that. So next slide. And same thing here, we show a monitoring of that, and the red being high vacuum, the shading to blue being lower vacuums. And again, we're allowing fresh air in on the truck dock side of the building, hard piping it all the way around to the other side. And that's just so we have hardly any evidence that the system is there. So next slide. This is a sub-slab depressurization system that a site that we're peripherally involved in. There's 30-some extraction points, and they're all plumbed at 3 separate blowers. And so for some of those systems, one thing I wanted to point out for a depressurization system and other systems, you typically are going through this pre-mitigation testing, a pilot test of some kind. How much vacuum can we get? How far will it extend away from that point where we are extracting air and applying a vacuum? And one thing to really make sure when you're doing that is that all the other systems that may be in a building, this is especially true for existing buildings, the heating, ventilating, and cooling system, maybe some other kind of makeup air or exhaust air systems, make sure that those things are on. We did have a site at one point in time where the pre-mitigation testing showed one thing, the system was installed, there were some renovations going on in the building, a new HVAC system was installed, some other exhaust. All of a sudden, the pressurization system was not sufficient to get to the operational metrics that were needed. Additional points had to be put in, and I think a larger fan had to be put in. So again, a lesson learned. Next slide. So these are just some pictures showing some engineering drawings, if you will, taking the building construction drawings from the architect and the engineer. For those of you that are in southern states, you may be saying, why is that footing down so low? We have frost depth footings. This was a site in Minnesota. And so this was a case of a truck dock. So there's pavement down there 4 feet below the finished floor elevation, and then the footing another 48 inches or so below that. So again, trying to not have evidence of our systems. There's the screened vent cover on the fresh air inlet. If you go to the next picture, here's a picture of what that might look like on the outside of the building. Next picture. Same thing with a fresh air inlet where we need to have it. It's going to be an at-grade wall. And what that might, next picture is what that might look like in a green space. At one point in time, we had PVC pipes. This one is steel. And where there's lawn right up against the building, the lawnmowers run into the downpipe. So we went from PVC to steel. Next picture. Whether you've got an SSD or an SSV system, you typically have riser pipes up a column in a building, up a wall, a pipe chase, and you got to get that pipe up, typically to the roof. Not always to the roof, but typically it is. A couple things to point out. This was a project where we were keeping everything a little bit lower. If this was the sort of during construction, that pipe up might be left open for a while, and you wouldn't believe what contractors happen to throw in that pipe if they were walking along, and there it is. Cigarette butts, rags, you name it. So anyways, you need to protect these things. Again, it comes back to the planning and the communication. Next slide. And here's what it might look like. This was a brand new building. It was a warehouse building, and we're rising up next to a column. Sometimes, depending on how much clearance there is between the floor and the piping and the membrane, those interior columns need to be lowered. So in this building, I think we lowered 3 of those columns because we had this, actually no, this was the passive system. And so we ended up lowering 9 of those columns to allow the piping to come across over to the column and then rise up so that it's literally right next to that box girder. Next slide. The thing we find out, you couldn't see it in the last picture, and this is a different site, but we need to protect those because typically it's PVC pipe, in this case protected with a steel collar. Fork truck drivers see these things and they want to hook them. I don't know why, but they seem to be. So up on the roof of the building, you might have a rotary roof vent for a passive system. We found in cold climates, that's not such a good idea because these are not very robust, and the humid air from below the building will form condensate and will freeze up. And that can be a big problem when the system doesn't work. Next slide. So this is a discharge from an active ventilation system in a small building. And what you see is a no-loss discharge stack on that riser. This is above the fan, which is down in the mechanical room just under the roof. And one thing I wanted to point out here is it's very high because we went through calculations of what height of a discharge would not allow vapors to generally be reintruded into the building through makeup air inlets or through the doorways. And most guidance documents will tell you, hey, you need to be 10 feet from an air inlet, or you need to be 2 feet above the roof parapet or the apex of the roof. But that doesn't tell the whole story and is really not proper design. I'll show you a nomograph here in a minute how you arrive at where that should be. This again is an active it says active vent system, but it could be an SSV system. And there's a radon style fan there. Some of these systems are very similar to a radon system. And in this case, we are putting that no loss stack on there, which is a very prescribed design because it keeps the rain out as long as the airflow velocities have a certain minimum velocity. And people have tried other ways to keep rain out, other types of caps, other types of angled piping and so forth. But this works, and the reason it works is because rain doesn't fall straight down. It's always falling at it. Next slide. And here's a little nomograph that one goes through to figure out where should your discharge stack outlet be so that it doesn't get entrained into doorways, into windows, into fresh air inlets. And it looks a little complicated, but you work through it and you figure out at what height should that be? Because this is a source of VOCs. They're very dilute, but they are a source of VOCs, which eventually get broken down under the influence of the sun's rays. Next slide. So just two last things. This is the blower that was used for the 200,000 square foot building, fractional horsepower blower. It has a silencer on it. So it was about 200,000 square feet. Next slide. Next slide, my last one, is a system that's providing for mitigation in a large industrial building. About 200,000 square feet plus is the area. It's partial building mitigation. So the rest of the building, it's about 500,000 square feet. This is a 10 horsepower blower. So it's providing mitigation, and it's really a sub-slab depressurization system, no fresh air in. And I needed 10 horsepower blower to do that. The other one, I was using a fractional horsepower blower. So it just kind of shows you perhaps the benefit where you can allow fresh air in, because it just generally allows for less energy input to get the air. So that's my presentation and a few items of lessons learned.
Chris, I have to say,
Yeah.
you win the award for going through the most slides with the best timing ever. That was amazing. So, great job.
Oh, I planned it down to the second.
You nailed it.
Of course.
Congratulations.
We're engineers. That's what we do.
And
I'm sure everybody's getting hungry, so I don't know if we have any questions or.
I think we do have one question, actually.
So we have time for one question. Someone from the audience asks, are air permits required for the potential VOCs being discharged from active venting systems?
So I have had some situations where we've gone through the process of looking at air emission, the mass emissions, to only to find that we don't have the mass emissions that would require it, or we can dial down the system so that we won't have the mass emissions that require it. I have to tell you, in the city of Minneapolis, and I could be wrong, I mean, somebody in the audience will probably correct me on this. I think that you need it for an active system in Minneapolis, or you used to. And it's been a while since I've done one in the city of Minneapolis proper. So, and there are probably cities that do have that requirement. Again, the emissions of a mitigation system are usually quite low from a mass standpoint. If you were to calculate how much is being emitted over the course of a year or whatever.
Yeah, I think in Texas it's similar. We have a permit by rule system where you go through the appropriate calculations and try to determine if you exceed the kind of PBR VOC discharge limits. And as Chris mentioned, you often try to design your system so that you moderate the flow such that your discharges are below those limits, and therefore you don't need a more extensive permit. So I think that's typically how it's worked for remediation systems.
It is something to look at. Other components of the system may also require permits. Building inspectors many times don't even know what they're looking at when they're coming to look at these systems.
Sure.
Other times they have certain requirements. I know in the city of Minneapolis, we've been made to go from PVC to steel piping as if we have multi-story buildings, and I want to say it's over 3 stories, where we're rising up to the roof, and so that's an issue. And so in other words, you need to look at permits, not just for emissions, but other components of the system. It might be an electrical permit for your control panel, so something like that. So.
Okay, well, great. There's a lot of information, and so great job, Frank and Chris, for doing this. If you have any questions and you want to reach out to these guys, you can. There's their contact information. Happy to answer any questions that you may have. And I think our next webinar for next month is environmental conditions for financing affordable housing development. So we have Stephen Jansen and Derek Schilling. They're going to be our experts for that one. So we want to thank you for joining us for this webinar. And if you have any questions, send them to myself, Lydia, or Frank and Chris. Guys, thanks for joining us today.
Thank you.